How are you all doing? Good. How many of you have been with me this past 3 lectures? 2 days, my first 2 lectures. Okay. So everybody, you have been here last 3. How many of you were here last lecture? How many of you are just joining us today? Wow. Big number, large, okay. All right. Okay, let me introduce myself. My name is Patrick Mensah, as you see. I'm a professor at Southern University in Baton Rouge, Louisiana, in the Department of Mechanical Engineering. And I am here under the auspices of the Carnegie African Diaspora program, working in collaboration with my host, Dr. Patrick Boakye, chemical engineering that most of you know. As part of our work in the Carnegie African Diaspora program, which is to work on the computational fluid dynamics of cloud microphysics and dispersion of pollutants, we decided to give you this mini-series introduction on computational fluid dynamics. And so in our first lecture, we introduced the computational fluid dynamics and talked about the what, the why, and where. That is, what is computational fluid dynamics, and why its importance, and then where it is applied. And so for those of you who were with us in the first lecture, can I call upon you to tell us what is computational fluid dynamics? And please speak up, okay? I'm sorry, sir, but you know how we do it. I want those at the back to hear. So, you need a microphone? No.
Okay, so my understanding so far, computational fluid dynamics is the use of computer application, and Prof mentioned some of them, like ANSYS and other softwares to model real-life problems involving the flow of fluids. So, example is the flow of wind on aircraft and many other examples that Prof gave here. So, yes, that's my understanding so far.
Okay, thank you. So we use computer programming together with the fundamental governing equation of fluid dynamics to basically analyze by simulation various engineering applications where flow processes occur. Now, in our second lecture, we talked about modeling. And the question is, why modeling? Because we know that in computational fluid dynamics, we said, well, we have to solve the governing fluid dynamics equations. Okay, what are those governing fluid dynamics equations? They are the conservation equations of mass, conservation equation of momentum, conservation of energy, and conservation of fluids. Okay, so in the last lecture, we sought to delve a little bit in detail in reviewing what those governing equations are. Okay, in this lecture, and as part of my overall first lecture, I talked about the fact that, well, in computational fluid dynamics, after you have obtained the governing equations, okay, you need to basically discretize your computational domain, your region in space that you are doing your analysis, and then come up with some computational scheme, some numerical scheme to basically help solve your problem by developing an algebraic set of equations that will be solved using numerical methods. If you recall, there were 3 approaches that we said that you can you can use in developing the numerical scheme for solving computational fluid dynamics. What are those three schemes? What are those three approaches? One was finite difference methods, the other was finite volume methods, and the last was the finite element method. Okay? Recall that we said that we could develop structured and unstructured grids for all these different applications. Today, our focus is on developing the numerical methods based on the finite difference scheme. Okay? And then I'll quickly try and wrap up with an actual application that one of my graduate students worked on for his master's thesis. Okay? Okay, so in this presentation, I'm going to introduce you to the numerics of finite difference methods. Okay, we will specifically talk about how to apply the explicit and partially implicit and implicit approaches to discretizing partial differential equations. I'll talk briefly about finite control volume, and then once we've obtained our complete set of equations based on whether either the explicit or implicit approach, then we'll use a solver such as the tri-diagonal matrix solver system, traditional called the TDMA system, to solve the set of equations that results. Of course, there are invariably some error or some stability issue, which I'll comment on. But before I go into the finite difference scheme, let me just go over this brief classification of differential equations. Now, these differential equations that you see were derived from simplifications of the energy equations that we derived yesterday. Okay? Yesterday we saw the energy equation under steady state conditions, okay, where the left-hand side of the energy equation, that is the rate of change of energy, whether internal or kinetic energy with respect to time basically is dropped, okay? That part of the energy equation goes away, and also the advection part of the energy inflow into the system or outflow, that net rate of energy inflow also drops out, and then on the right-hand side, you are just left with the diffusion term, okay? And you are also left with viscous energy dissipation term. Now, the viscous energy dissipation term basically drops out, assuming that we don't have any viscous dissipation within the system, and then we also drop out any energy generation. With that, you are left with the so-called Laplace equation, okay? You may have seen this a lot in your differential equation class, okay? This is called the Laplace equation. Laplace equation is nothing but what we also classify as an elliptic equation, okay? It is the two-dimensional, second-order two-dimensional equation in terms of x and y of the temperature. All right? And then another classification of, so in essence, any equation that you see of this in this form is classified as an elliptic equation. Okay? You can add the third term to it if it's three-dimension. That is the second derivative of the temperature with respect to the z direction, and it's still an elliptic equation. Okay, but this is just the two-dimensional form. A parabolic equation basically has the time rate of change of temperature now maintained. Okay, you have the time rate of change of temperature now maintained for a parabolic equation. On the other hand, a hyperbolic equation, okay, you see now it has a second derivative of the temperature with respect to time. Okay, so these are different classifications of differential equations, and depending on your simplifications of your governing equations, you can basically reduce it to any of these types. So let's assume that we have one of these types of differential equations. The next step in developing a CFD, a computational fluid dynamics solution, will be to first discretize the domain, okay? And we'll see how to discretize the domain in both directions, and then use the domain to discretize the governing partial differential equations to obtain algebraic equations and apply the boundary and initial conditions, if any. Okay? Let's look at this carefully. Okay? And let me just go back. Of course, in the case of an elliptic equation, which is under steady state, there will be no initial conditions that is desired in solving this equation. On the other hand, for the case of the parabolic equation and the hyperbolic equation, there are time derivatives. Okay? So you need initial conditions. It becomes an initial value problem. That is why in this step here, we are saying that discretize the governing partial differential equations to obtain algebraic equations and apply the boundary conditions and or initial conditions as necessary. Okay? Once we've done that, then we solve the algebraic equations using our computational resources. In doing that, we have to monitor the solution for convergence. Obviously, if the solution is showing that the residuals are not converging, then that means we have a problem. You're not going to get the correct result, or your solution will oscillate forever, and so you will not get a good solution. And the fifth step here, we need to validate our solution, okay, to ensure that we are not getting bad results. Okay? We need to validate our solution against some benchmark data to ensure that we are getting very good results. Okay, so what we mean by discretizing our partial differential equation? Well, what we mean by that is saying that we are going to replace the partial differential or the integrals in the governing equations with discrete numbers. Okay? We are going to do that by replacement with discrete numbers. So we discretize the PDEs using either the finite difference method, the finite volume method, or the finite element method. Now, there are some cases, because of the geometry, okay, we may need some form of coordinate transformation and grid system, and so this is usually applied in the finite difference scheme. Okay, so let's take this rectangular domain. This is my y-axis, okay, and this is my x-axis. I am going to discretize. When I say I am discretizing this rectangular domain in 2 dimensions, that means I'm going to discretize or subdivide my region into equal spaces of delta x, okay, delta x column-wise, and in the horizontal direction here, the rows, I'll have equal spacings of delta y. All right? And so I discretize my domain. Now, in the case of finite difference methods, what we are interested in is in the solution of the partial differential equations at these grid points. Okay? At these grid points or nodes throughout this computational domain. So we want to find the value at this point. We want to find the value of the, say, temperature at this point, or the value of the velocity, temperature, and so on, the dependent variables at all the grid points within the domain. Any comments or questions? So we have discretized our domain. We have labeled it accordingly. Note that right for now, in developing my finite difference equations, I'm going to note this point here as y sub j and x sub I. Okay, and so the node to the left of I will be what? I minus 1. Okay, and the node to the right of it will be I plus 1. The node to the top of it will be j plus 1, and the node below it will be j minus 1. Okay? All right, let's look at how we are going to do this. In representing our derivative terms with discrete algebraic equation, we use the Taylor series expansion. Okay? When you took your calculus class, you may have come across the Taylor series expansion. And the Taylor series expansion of a function, for example, x plus a, is given by the functional value, the function evaluated at x, plus the first derivative of the function times the increment that is desired, which in this case is a, divided by the first factorial of it. Okay? Plus the second derivative of the function times a squared divided by the second factorial. Okay? Plus the third derivative of the function times a cubed, okay, divided by the 3 factorial, and so on and so forth. Okay? That is the Taylor series expansion. We can also find the Taylor series of expansion of f of x minus a. The only difference is that now you see that, well, this a is minus, right? So in terms of the factor, in expanding the factorial, this will be minus a. So the first term here becomes f of x minus the first derivative minus of the first derivative divided by 1 factorial plus, this is plus because a negative squared is what? Positive. Okay, so this is now a plus divided by 2 factorial, and then a cube of a negative will be negative, so you have the third derivative a cubed and 3 factorial. All right? And so on. So really, we can find the Taylor series of expansion for any function. For example, we can find the Taylor series of sine of pi x, of this function, of this transcendental function, sine of pi x. And you can find it for 1.1, sine of pi times 1.2, which is given by this value, and you can check for yourself, okay? And you can also find the sine of 1.21, and then you can find the sign of 1.19. Okay? I will entreat you to basically do this, as a homework exercise up to 4 terms. Okay? And see if you can obtain these results. Okay? So in general, this is the Taylor series expansion of any function, and that is what we are going to use in developing our finite difference equations, converting our partial differential equations into an algebraic set of equations. Okay, so our interest is to replace the partial differential equation with a suitable algebraic difference quotient based on the Taylor series expansions. So, for example, if Uij denotes the x component of the velocity at a point, then we can expand for u sub I plus 1 as u of ij plus du with respect to x times delta x, because where's the 1 factorial here? 1 factorial is just 1, right? Plus the second derivative of u times delta x squared, okay, divided by 2 factorial, which is 2 times 1, right? Then plus the third derivative times delta x cubed divided by 3 factorial, which will be what? 3 times 2 times 1, so this is just 6, and so on and so forth. Okay? Similarly, we can find the u minus I1j, and so we basically obtain the Taylor series expansion for these 2 terms. Okay? And let me just go back and let you know, just review briefly. So what we are saying is that if we are looking for the velocity u, I, j at this point, we are using the Taylor series expansion to represent the velocity uij at this point as we've shown. Okay? And similarly, we can use, we can find the velocity ui plus 1 for this point and the velocity ui minus 1 at that point using the Taylor series expansion. So from the Taylor series expansion, then, well, how do we now replace the derivative terms in our governing equation? How do we replace our derivative terms in the governing equations? So if you look at this equation, okay, let's look at this first equation. Okay, if we basically subtract u minus ij from both sides of the equation, okay, and also take all these terms here, all the remaining terms of our Taylor series expansion to the left-hand side of the equation, then we'll have left alone the partial of u with respect to the partial of x times x, okay? And so if we come here and divide through by delta x, okay, we have ui plus 1 minus uij divided by delta x minus all the remaining terms divided by delta x. Any comments or questions? Okay? If we lump all of these terms together as basically having the order of delta x, okay, that is really what we call our truncation error, okay? That means this will be the error we would obtain in representing this partial derivative of the velocity with respect to x by this term here. Okay? This is the error that will be obtained if we represent the partial derivative by just this term here. Okay? So wherever we see the partial of u with respect to the partial of x in our governing equation, we are going to represent it with this finite difference form. Now, another approach to coming up with the derivatives in our finite difference equation is to use either the backward difference or the central differences. Okay? In order to obtain the central difference, okay, what we do is we subtract this equation, okay? We subtract this equation from the top equation. Okay? If you subtract these two equations, obviously these two terms will drop out, right? And since you are subtracting, these two terms will have to do what? Add. Okay? And so let's look at the simplifying result. The simplifying result is such that, well, since you end up adding that derivative term, now you see that it's 2 times the partial of u with respect to x, okay, and so forth. Okay? Now, if we divide both sides of the equation by 2 times delta x, then you end up with this equation 5, and all these terms that are left over are what we call the truncation error, or now it's the order of magnitude of the error will be of delta x squared. It's second order of magnitude. All right? So we found another way of representing this derivative here using what we call the central difference. And in summary, okay, these are what we call the so-called 2-point formulas. And just as we derive the first derivatives in the x direction, we can also derive the first derivatives in the y direction. Okay? And so the forward difference for the partial of u with respect to y then can be obtained with this forward difference equation, this backward difference equation, and this central difference equation. All right. So that takes care of the first derivatives. Now, let's go back to our 2 initial equations that we started out with, okay? On the other hand, if instead of subtracting, we add these 2 equations together, okay? If we add these 2 equations together, then you see that, well, you end up with what? ui plus 1 plus ui minus 1, okay, on the right-hand side. But on the left-hand side, you have what? 2 times what? ij, okay? And then plus 2 times the partial of u with respect to x, and the partial, 2 times the partial of u with this, no, these two terms cancel out, okay? Because this is what? This is plus and this is minus. This cancels out, okay? So now you end up with this second derivative term, which you see here. Okay? When you add these 2 equations together. Okay? So now you can obtain also an expression for the second derivatives, or second differentials, both for this is the x, okay? And for y, in the y direction, note that now this is what? Uj plus 1 minus 2ij plus uij minus 1, and it's order delta x squared and order delta y squared. Okay, so now we have expressions for the first derivatives and the second derivatives. And then in this case, we now want to look at mixed derivatives, the finite differences to obtain the mixed derivatives. The mixed derivatives are, for example, taking the partial first with respect to the partial of the velocity with respect to x, and then taking the second derivative of u with respect to y. So this obtains the mixed derivative, okay? And sometimes the governing equations can have mixed derivatives, and so the question is, how do we represent those mixed derivatives when they occur in the governing equations? And so this approach is just giving us a way of using the Taylor series expansion to obtain mixed derivatives from the finite difference equations, okay? So taking the derivative of ui plus j and uij, that is of the Taylor series expansion, okay? You take the derivatives of the Taylor series expansion, and then now you subtract them. If you subtract them, you will end up with these mixed derivative terms that now you can subtract. And going through the algebra, you see that you end up with this expression, okay? However, when we come here, okay, and let me just slow down and go back. Well, so what are we doing? We are saying that we are solving for this, right? If we solve for this, this will be, you divide this side here by 2 times delta x, and all these other terms becomes higher order terms. And so we have du dy I plus 1 minus du dy I minus 1j divided by 2 delta x and plus all the higher terms. But we already know this forward difference term, okay, from the first derivative, right? And we already know this. We already know this forward difference equation, and we already know this backward difference equations. So we can now just substitute for this term and substitute for this term, and this will be the resulting equation for this mixed derivative. All right? All right, so once we have obtained the finite differences for the different modules, then we have to think of what happens at the boundaries. There is a figure that is not appearing. Okay, yes. Yes, we have gone through all these derivations. The point is understand how they are derived and where they are coming from. But for the most part, you can find a lot of references where these finite difference formulations have already been put in nice table forms. Okay, so you can basically use the tables to pick the necessary finite difference representation that you need to discretize your governing equation or your conservation equations. Okay, so that is what this slide is saying. Okay, and these are for the first derivatives. Okay, this represents the second derivatives. The second derivative, this is the central difference for the second derivative. This is the forward difference in y, and this is the backward difference or the rearward difference in y. You have mixed derivative terms, okay, the mixed derivative terms, and so on and so forth. And here, now the question is, okay, we can now represent the internal nodal points by any of these equations. Okay, we can represent the internal nodal points within our grid. Okay, so long as we know that we are at this point, then we say, and if it's the second derivative we desire to replace, then we substitute with this. If it's the first derivative at this point that we need for y, then this is what we have to replace with in our equation, and so on and so forth. Now, but what happens when we have a boundary? Okay, a boundary node such as this point. Okay, how do we represent it? Well, that boundary node basically depends on the boundary conditions. I'm not going to hold you into this, so let me just skip it, okay? And say that, and I'll get back to the boundary conditions, okay? But just to say that, for the forward differencing scheme or the backward differencing scheme, are desired for the boundary conditions depending on the problem. Whether you have a fixed temperature or a fixed no slip condition at the boundary, and so on. And then in general, an nth order polynomial will give you an nth order accuracy. Okay. Also, a first order derivative will give you an n-1 order of accuracy, and a second order derivative will give you an n-2 order of accuracy, and so on. Now, once we have replaced all our derivatives in our governing equations and basically also impose our boundary condition, what about the time derivative? Okay, what do we do with the time derivative? What I showed basically took care of the spatial derivatives in x and in y. But what about the time derivative in the case of a parabolic equation and in the case of a hyperbolic equation? Well, for the time derivatives, you can basically use it's as if this is, well, for the time derivative, you can basically march forward in time, that is using the explicit approach, or use the implicit approach, okay? Marching forward in time basically saying that I'm going to use the known properties at the time level n to find the properties at the time level n plus 1. And then once I know the properties at this level, I'm going to use in finding the values at the time step n plus 2. Okay, that is time matching direction. Okay, the explicit approach. Okay, so let's look at this the heat diffusion equation. Okay, we can basically convert the whole of this heat diffusion equation, the time-dependent variable, the temporal variable of temperature, we can do it explicitly or implicitly. Okay, using the explicit formulation basically means that, you know, you're going to use the known values at time step n at the nodes I minus 1, I, and I plus 1 to determine this node ij here at the next time level n plus 1. Okay, that is the explicit approach. Or in other words, I'm going to use my initial conditions. If I know the time level at time 0, I'm going to use those as my initial values in order to find the values of my node at the next time increment. Okay? Whereas in the explicit approach, in the implicit approach, okay, rather you only have one known value at I. Okay? And that one known value results in 3 unknowns, okay, that you need to solve for. So it's implicit, meaning that really here you have to solve iteratively, okay, to obtain the solution at the next time step, whereas here you can directly calculate for the explicit method the unknown from known values. Okay, that's the difference between the two. Okay, let us just quickly revisit the boundary conditions. These are the different types of boundary conditions. The Dirichlet boundary conditions, that means known property value at the boundary, known, for example, known temperature or known velocity at the boundary. The Newman boundary condition means that you have, you know, the partial with respect to the normal at that boundary. For example, you know the heat flux at that boundary, okay? Or you know the heat flux, or whether that boundary is insulated. The other type of boundary condition is called the Robin boundary conditions. Robin boundary conditions normally results where you have, for example, you have some diffusion, some combination of diffusion plus convection at the boundary, okay? So you have an imposed temperature and you know an imposed gradient at the boundary. And then the mixed type of boundary conditions could have an either or, you know, flux or specified property at the boundary. Okay, so let us apply the explicit method to this heat equation. Okay, the heat equation is saying that the rate of change of the temperature within the medium is equal to the diffusion in the medium. Okay, this is a one-dimensional heat equation. So it's an initial value problem. To solve this initial value problem, of course, you need initial conditions and you need boundary conditions. Now, question, how many boundary conditions would you need for this equation? How many boundary conditions would you need? And why? How many boundary conditions would you need? Well, if you go back to your calculus, it's a second, the spatial derivative x is second order. Okay, so if it's second order, you need two boundary conditions. Okay, that means you need the boundary condition at one end of the domain. Okay, one end, say at x is equal to 0 and at x is equal to at the end of the domain. You need two boundary conditions. The time derivative is first order, so you need one initial condition. Okay, you need one initial conditions. And so to discretize the boundary equation, these governing equations, you see that we replace this term, the time derivative, with this explicit form of the finite difference equation. That means that, remember, we said in the explicit form, you are going to obtain the value of the next time step based on the old time step. So n plus 1 is the new time step, and n is the old time step, okay? Divided by delta t, that is your temperature, your time difference, and then plus higher order terms. And then for the second derivative, for the second spatial derivative, we replace it with the following central difference for the second derivative. Any comments or questions? Okay, so that is our replacement equations. And once why is this not working? Oops. Okay, so once you set up your equation in this form, then you can basically simplify it, okay? Simplify it such that you end up with this formulation where you calculate, okay, basically what you're doing is you're going to simplify it by solving for Ti at time step n plus 1, okay? You solve this whole equation for Ti n at the time step n plus 1, and that is this equation here, okay? Where this F multiplier is alpha delta T delta x squared, and then the multiplier over here, 1 minus 2 fx, and fx, of course, will be that, and so on. Okay, so this gives you the explicit solution to the temperature at the time step n plus 1. Okay, the explicit method. So in order to obtain the solution, so long as I know the initial temperatures at Ti, right? Ti minus 1, Ti, and Ti plus 1, I can always find the temperature at the next time level n